Yo, 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 yo. What's up, everybody? Especially all you band geeks out there. I could say band geek because I was one, all right? And be proud of it, all right? You play saxophone, you're short like me, but you just gotta own it, okay? Band is cool. At least in my eyes it is. I love it. But maybe you're not a band geek. Maybe you're just watching this review. If that's the case, then that's cool too. But anyway, I want to catch you up on what we talked about this week, and I also want to apologize because I planned on posting this video earlier, but I've been under the weather. I'm sorry. I've been kind of sick, and you can kind of hear it. But you know what? Sickness doesn't stop science. There it is. Quote of the day. But let's talk about something. Heat. All right. We got heat to talk about. Heat, thermal energy, temperature. I want to define each of these and talk about what exactly they mean in the physics realm. So here, dying. We got uh, a beautiful, beautiful picture of Prince Zuko, and I hope you know who that is. He's from Avatar. All right, he's a firebender. What would you rather be, a firebender, waterbender, earthbender, airbender? I would be an airbender. Why? Because it's cool. All right, remember when we did tug of war in class? Remember when we did that? It was a lot of fun, right? But what happens if you hold a rope like this guy and you yank it out from his hands, but he lets the rope kind of go through? Well, his hands would burn. Why? Why would his hands burn? Because of friction, right? Friction. Friction causes thermal energy. It creates thermal energy. Some of that energy, that kinetic energy of the rope moving, gets lost due to friction in the form of thermal energy. Now, I want to define this. Thermal energy is the total kinetic energy of the particles of an object. Now remember, from last unit, kinetic energy is the energy of motion. It's the energy of moving objects. Well, are particles moving? Yeah, at the very tiniest level, particles are moving. They're moving around. Um, and thermal energy is the total kinetic energy of all those particles moving. Now let's take a look at this example. We got a teapot. What I did was I searched beautiful landscape teapot, and that's what showed up, that beautiful picture. All right, I don't know who took that. But thermal energy depends on the mass and temperature of an object. You might remember we did a lab right before um, you the band people left on this trip. I hope you're having fun. We did a lab where you mixed hot and cold water together and you recorded the temperature. Well, you used less and less cold water each time. What did that do to the final temperature? Well, it raised it. There was more and more heat. There's more and more thermal energy in that final mixing, the less and less cold water you use. Well, that makes sense. The less cold water you mix with warm water, the hotter it's going to be. So that's what we mean when we say thermal energy depends on the mass, so how much water you used, and the temperature of an object, okay? The more mass something has, the more thermal energy it has. The more temperature, the higher temperature it has, the more thermal energy it'll have, okay? So thermal energy is very important. Heat, by physics definition, is the transfer of thermal energy from one object to another. Heat is transfer. When I say heat, you say transfer. Heat. Very good. It's a transfer of thermal energy. So in this example, what do you got? You got you got logs, you got a bonfire. I hope you've had a bonfire already. Bonfire. And what's being transferred? Thermal energy from what to what? Well, the thermal energy from the fire is being transferred to the marshmallow. Are you the kind of person that puts the marshmallow right in the fire and burns it? If you are, shut this video off. You get an F. Just kidding. But that is heat. It's a transfer of thermal energy. Okay? Have you ever been in a hot tub? Hot tub, you get out in the cold after you're done soaking it for like 2 hours. It's the winter time. You get out. What happens to your body? It's steaming, right? Well, what's going on there? Heat, as in thermal energy, is being transferred from your skin to the air. That's why you're steaming, okay? Heat is that transfer. Heat is transfer. It flows from hot to cold. Your skin is hot, right? From the hot tub, you were just soaking in water, and it transfers that thermal energy to the air around you, and it becomes warmer. Do you understand that? I'm asking that question as if you're going to reply. Do you understand that? Very good. Now here we got an amazing slide. Temperature, on the other hand, is how hot or cold something is. It's a measure. You've used that your whole life. There's 3 scales: Fahrenheit, which we use here in America. There's Celsius, which the rest of the world uses because it makes more sense. And we got Kelvin, which is a measure. Its base, 0 degrees, is called absolute zero. Well, what happens at absolute zero? You might have heard about it before. Theoretically, it's when all motion of every particle stops. So all the particles deep down at a microscopic level, they stop moving. Well, guess what? That actually can't happen. Scientists have got so close, but it doesn't actually happen. Why? Because of a reason that you have to get into quantum mechanics and a bunch of nerdy stuff. But really, we've come so close, like a billionth of a degree of Kelvin of absolute zero, but we can't reach it. It just doesn't happen. There's always some sort of energy, okay? But Kelvin is a scale that baseline, that 0 degrees, is absolute zero. And we use that in really nerdy sciences like physics and chemistry. But really what I want you to understand is the Fahrenheit and Celsius. Here we go, this table. The boiling point of water in Fahrenheit is 212, okay? Which doesn't make sense. Where we get 212 from? I don't know, America. And we got freezing point of water, 32 degrees. Where we get that? I don't know. But these are 2 numbers that I think are very, very helpful and necessary for you to know. Because why? Well, we use Fahrenheit here in the US, all right? On the other hand, the Celsius scale makes it very simple. The boiling point of water is 100 degrees. The freezing point of water is 0 degrees, okay? So Celsius is a lot easier to use because it has these benchmarks that make a lot more sense. Fahrenheit, on the other hand, doesn't make that much sense, but we're stuck using it anyway. Why? Because we're America. And then Kelvin over here is the same as the Celsius scale, okay? A degree in Kelvin is the same as a degree in Celsius, except it's 273 degrees more. So basically, if you know your temperature in Celsius, you can just find your temperature in Kelvin by adding 273. kind of weird, but it is what it is. And then lastly, let's talk about what temperature is and how it's actually related to thermal energy and heat. So temperature is related to how much average kinetic energy there is in the particles of an object. So remember, before we were talking about thermal energy. Thermal energy is the total kinetic energy. Temperature is average. Well, let's talk about the difference there for a second. Let's say that you've got a cup of coffee, right? And its temperature is 100 degrees. All right. Let's say you've got a bathtub of coffee. Which one has more thermal energy? They're both the same temperature. Let's say they're both the same temperature, but you got a cup versus a bathtub of coffee. Why do you have a bathtub of coffee? I don't know. I'm just an example. Which one has more thermal energy? Well, the bathtub does. Why? Because it has more mass. Remember, thermal energy depends on mass, okay? On the other hand, I can ask you the question, what has more thermal energy? A cup of coffee, which is, piping hot, or Lake Erie? Well, that becomes a much trickier question because Lake Erie right now is very cold, all right? It's not freezing, but it's cold. The answer is actually Lake Erie. Why? Because it has so much more mass. If you threw that cup of coffee into Lake Erie, is its temperature going to change that much? No. Why? Because there's so much more thermal energy you'd have to transfer into it for its temperature to change. We look at total kinetic energy when we talk about thermal energy, okay? Now, that's the difference between temperature and thermal energy. There is a cool, let's see if we can run this from current slide. Yeah, there we go, it's wiggling. Now remember from last unit, kinetic energy is 1/2, what's the M? Mass, and V, velocity, very good. Velocity is what? Well, it's the motion, it's the speed with direction of the particles. Well, what's happening to the particles here as they heat up? Well, they're bumping into each other, getting faster, and it's moving down the line. It's moving from hot to cold. Remember, heat is a transfer of thermal energy from hot to cold. That's what we have here. And as an object heats up, the average velocity of the particles increases. Well, we can see that right here. The average velocity, it's getting faster and faster and faster. So what's going on? Well, the kinetic energy of these particles is increasing, and so is the temperature. The temperature is a measure of the average kinetic energy, remember? So the temperature is increasing as you go down. As this GIF plays, it's increasing in temperature from left to right. All right. So to summarize, look at me. All right. Thermal energy. It depends on temperature and mass. Okay? Depends on temperature and mass. Temperature of coffee is piping hot, but a pot of coffee has so much more thermal energy than just a cup of coffee because it has more mass. All right. Likewise, when you have Lake Erie, it's so much more mass, it's going to have much more thermal energy technically because you're adding up all the different kinetic energies of every particle in Lake Erie. It still has more thermal energy than a piping hot of coffee, even though they are vastly different in temperature. Temperature is the average kinetic energy. So you could have the same temperature of coffee as you do in a pot of coffee, but what's different? The masses are different, therefore thermal energy is different. All right. Temperature is the average. Average. Thermal energy is total and heat is transfer. Okay? So those are the three terms that we've been talking about. Have fun. Have fun on the rest of your trip if you're in band, and I'll see you soon.